Hi, this is the presentation of AC Analyzing Circuit by Group 8. The members are AMIRA BATRISYIA, JESSYIANA, AINA AFRINA and FARIS HAZIM. This part 1 will be explained by FARIS HAZIM. There are 4 main objectives in this PBL. 1 is to understand the calculation. The understanding to use Ohm's law, power triangle, and phasor diagram can be improved. The second objective of this PBL is to understand more about the simulation. With the help of MultiSim software, we can get more accurate value than calculation. The next objective is to understand the concept of power factor correction. Before power factor correction, the value of voltage drop will be higher, the value of current will be higher, and the power factor value will be away from 1. And after power factor correction, the voltage drop value will be lower, the current value will be lower, and power factor value will be closer to 1. The last objective of this PBL is to understand the application of power factor correction. This power factor correction is applied in transmission line and power plant. This power factor correction application will benefits to both consumers and distributors. Part 2 of this presentation will be explained by JESSYIANA.
The measure of electrical efficiency is known as power factor. When shunt capacitors applied in industrial power system, therefore power factor correction. Benefit 1 is reduced power bill. Capacitor reduce power bills by reducing the kVA or kVAR demands. Benefit 2 is gain in system capacity. If a system has an existing overload, the capacitors may eliminate it. Benefit 3 is improve in voltage conditions. An estimate of voltage rise from the installation of power capacitors to a factory electrical system can be made. Technical advantages of power factor correction in electrical plants. Better utilization of electrical machines, better utilization of electrical lines, reduction of losses, reduction of voltage drop, and in industry application, power factor correction can be found in transmission line and power plant. In the machine, it can be found in transformers, and alternators, voltage motors and multi-speed motors, which failure to do so may result in damage to the motor.
Part 3 of this presentation will be explained by AMIRA BATRISYIA.
To measure the total impedance, the sources and ground must be removed. If your source is current source, it must be open circuit. And if your source is voltage source, it must be short circuit. Ground also must be removed. If not, the value that you get will not accurate. The tool to measure the total impedance in MultiSim is impedance meter. You can get the impedance meter on the right hand side of the screen. Place it at your circuit. There are two polars, which is positive and negative. Click on the positive polars of the impedance meter and connect to the resistor. Then, the negative polar of the impedance meter connect to the bottom of the circuit. Run the program. Then, double-click on the impedance meter. As you can see, the frequency is 60 Hz, but frequency for our circuit is 50 Hz. So, we must change to 50 Hz. Close the box and stop. Rerun the simulation again. Double-click on the impedance meter. Now, the frequency is 50 Hz, which is same as the frequency value that we insert in our voltage source. The value of the total impedance shown in the box is in real and imaginary. Therefore, the total value of R is 0.299 and the total value of X is 0.1149. So, this is how to measure impedance in AC circuit in multisim. Next, I will demonstrate on how to measure current and voltage in multisim. For example, to measure current at load 1, click current probe which is available on the top of the screen. Place the current probe at the current line of load 1. As you can see, the probe for this current is PR1. Next, take differential voltage at the probe and place the positive probe at the top of the load and place the negative probe at the bottom of the load. The probe for this voltage is PR2. Then click single frequency AC. In frequency parameter tab, the value of the frequency is 50 Hz, which is the same value of frequency in voltage source. At the output box, choose magnitude and phase. Next, click the output tab. As you can see, the PR1 for current and PR2 for voltage have been inserted into the right column. If you want to add another variable, search your desired variable at the left column and click Add. Then run. Then the output will be in magnitude and phase. To read the output, refer to the variable which is voltage and probe which is PR2. So this shows the voltage drop at the current load. The output for this voltage drop is 280.47 and the phase is 21.03. So this is how to measure current and voltage in AC circuit in multisim. Lastly, I will demonstrate on how to measure apparent power S, reactive power Q, and real power P in multisim. For example, to measure S total, Q total, and P total, click current probe and place at the current total. Next, click at the differential voltage. The positive probe place at the top of the voltage supply and negative probe placed at the bottom of the voltage supply. The probe for current is PR1. The probe for voltage is PR2. Next, click single frequency AC. In frequency parameter tab, make sure the value of frequency is same as the value of frequency in voltage source. In the output box, choose real imaginary as the output format. Then click Output tab. The variable of I PR1 and V PR2 are automatically added to the right column. To find S total, we can use the formula S equal to V voltage multiply I conjugate. To add formula, click Add Expression and choose PR2. And for multiply, choose star. And for the current is current conjugate, so search conjugate in function column. Click complex and choose conjugate. In the bracket, we insert I current PR1. Then click OK. Let's run the program. As you can see, the single frequency AC, the output is in real and imaginary format. This is the current total. Next is the voltage total. And the third is the expression that we had earlier. Based on the formula S equal to P plus JQ, we can know that the real power is 270.32754 K and the reactive power Q is J103.86576 K. So this is how to measure apparent power, reactive power and real power in multisim.
Part 4 of this presentation will be explained by AINA AFRINA.
There are 4 steps to calculate power factor correction system design. Step 1. Before power factor correction. Find the real power, apparent power, and reactive power. Construct power triangle. Identify whether power factor is lagging or leading. For step 2, after power factor correction, know the desired system power factor. Identify whether power factor is lagging or leading, and find the real power, apparent power, and reactive power. Construct power triangle. For step 3, combine and draw the power triangle for before power factor correction and after power factor correction. Calculate the reactive power capacitance. Find the capacitance and also capacitor value. Step 4. The last step. Prove the derived value for after power factor correction theta. Theta is reduced, the reactive power and apparent power is reduced, while current needed by load also reduced, hence losses in system also decrease.